G'day chemistry students. This first video has us begin module 6, which is all about acid-base reactions. Our first video covers dot points 6.1.2 and 6. Our focus is going to be on the properties of acids and bases, as well as how we actually define them, what chemicals constitute as an acid or a base. Let's get into it. So first off, I have a quick table with some properties of acids and bases. A lot of the first properties are observational and have been known, or at least recorded to have been known, since the time of the ancient Greeks. They began to classify certain substances and found that there are a lot of substances that were sour in taste and bitter in taste, and were given names that were appropriate. Those sour substances were known to be strong smelling and give a burning sensation, and could also at times feel sticky, whereas bases were generally odorless and slippery like soap. Bases in particular were quite well known. It could be found in lots of naturally occurring places and were used to make soaps and the like. Beyond that, though, what we know about acids and bases is that pretty much all acids are soluble, whereas for bases, there can be varying degrees of solubility. Some substances are very soluble, others are not. Both, when in solution, are conductive in solid states. They're not just like any other kind of ionic or molecular substance, generally not so conductive. What we also know as a property is how they interact with chemical indicators, acid-base indicators in particular. Now, these are things that you would have used and seen in year 9 or 10. But the basic idea here is that acids will turn acid-base indicators one certain color and bases will turn it another color, litmus being a common one. So blue litmus will turn red for acids, red litmus will turn blue for bases, and for any other indicator there'll be characteristic colors. We may also have an idea of this concept of pH, that acids have a pH less than 7 and bases have a pH more than 7. We'll break that concept down in a lot more detail in this course. We also then have different kinds of chemical reactions. Both acids and bases can be considered corrosive. They can cause chemical burns and damage body parts. Acids can react with metals. It's known as an acid-metal reaction. We'll cover that in the future. Similarly, some bases can react with metals, but not all. Acids can neutralize a base when they react together, and bases can then in turn neutralize an acid. Also keep in mind that if an acid is undergoing neutralization with a carbonate, it will also produce carbon dioxide gas. Carbonates are sort of a family of bases. Bases can also have some reactions to break down fats and oils. We can then start moving beyond this idea of simple properties and start looking at how the definitions of acids and bases have developed over time. In previous topics in junior science and in chemistry, we've talked about the idea that definitions and theories in science can always evolve and change. The general concept being that when there's new scientific evidence put forward that suggests that the theory is wrong or needs to be modified, those modifications happen. When we're looking at acid-base theory, there's no exception to that concept either. What we have seen is that what we know and understand about acids and bases have changed as we have learnt more and more about what acids and bases are and what they can do. The first definition that we're going to be looking at is from a guy called Arrhenius. Arrhenius was doing a fair amount of work in the late 1800s around acids and bases and came up with this definition of his understanding of what an acid and a base was. And this was mostly by observing known acids and bases and what they do in a solution. And by his definition, he said that acids ionize in a solution to produce H+, and that bases ionize in a solution to produce hydroxide ions. And from there, Arrhenius was then able to develop some general equations to describe what acids do and what bases do. This idea of HA was developed, HA being hydrogen, the hydrogen which would be produced in solution, and A being the anion. When going into solution, the acid would form hydrogen ions and the anion as well. For the bases, we would have XOH. We'd have the cation X and the hydroxide going into solution and forming those two ions. And for all of the acids and pretty much all of the bases that were known, this definition was really consistent. We saw current known acids all had hydrogen and they were coming off in solution, and pretty much all of the known bases were hydroxides. So this worked quite well. But there were still some limitations, and that was mostly the idea of ammonia. Scientists knew that ammonia behaved like a base, yet there was no hydroxide present to form when ammonia was put into solution, so it didn't completely fit the definition. Furthermore, the definition didn't account for all solvents. We were only looking at aqueous conditions where water was a solvent. So for a lot of organic solvents, we saw that there wasn't dissociation or formation of ions that were happening. Thus, it didn't really follow the definition in all circumstances. Moving on, though, we start looking at the idea of Bronsted-Lowry theory. In this theory, they took some of the key ideas from Arrhenius and then changed the definition just slightly so that more situations, more different acids and bases could be included in the definition. So the definition then became that acids donate protons, and usually this is H+, to another substance, and that bases are able to accept them. And this very much describes what happens with acids and bases in aqueous conditions a hell of a lot better than the Arrhenius definition. This then also meant that our general equation was developed a little bit more. We had HA still, it was the anion and the hydrogen which was to be donated. So this is our acid here. And the hydrogen was being donated to the base, forming HB+. The anion that was left that was a part of the acid then is just an anion in solution. So some advantages. This worked with pretty much all the acids and bases that were actually able to dissociate and form ions. So if something could form an ion, this definition worked really, really, really well, certainly for the time. And the definition accounted for substances that could act as both an acid and a base. So there were some substances that people started to realize could have acid behavior and could have base behavior. And what that essentially means is they're capable of donating and accepting protons at different times in different contexts. This is a concept that we'll look at in a few more videos. But Bronsted-Lowry theory does account for those particular chemicals that can do both. However, there were still limitations. Not all acid-base interactions could be taken into account because there were some reactions that still didn't fit the definition here, which was that there was a donation and an acceptance of a proton. So first off, there may not have been a proton exchange if the solvent didn't actually allow the acid and the base to dissociate. Here we're still working in these aqueous conditions predominantly. These non-aqueous conditions weren't accounted for within the definition, and as well, there were certain acids and bases that didn't even need a solvent to react at all. So for example, this reaction here involving calcium oxide acting as a base, working with this sulfide ion, which would have acted as the acid to form calcium sulfate. It's an acid-base interaction, certainly as we know it today. Both of those substances behave as a base and an acid respectively, but it didn't follow all of the restrictions that Bronsted-Lowry theory had. In saying that, though, this is a really simple and effective theory that works with most acid-base interactions. And in fact, when we're looking at acids and bases in this topic, we're actually going to be using Bronsted-Lowry theory the most. We then start to move into this Lewis definition, a much more modern definition that includes all known acid-base interactions. So here we start looking at electron exchange. This definition that is here still works with these interactions that are covered by Bronsted-Lowry theory, but then cover a broader set of acid-base interactions that aren't in aqueous conditions. So by the definition, we're told that the acids accept an electron pair from another substance and that bases donate electron pairs to another substance. This is very advantageous because it still works with Bronsted-Lowry, but as I said before, we can look at acid-base interactions without worrying about the solvent or whether or not there is an exchange of a proton. So here in this diagram, what we can see is that when two waters interact with each other, one can act as a base and one can act as an acid. In this circumstance, what we see is that the acidic guy over here brings a hydrogen over to the base, forming hydronium and hydroxide. So proton donator, base being proton acceptor. But we can also look at that in the reverse. For this exchange to happen, the pair of electrons that is sitting on the base here has to be donated to the hydrogen that is a part of the acid on the other side. So here, these two electrons will form a bond with the hydrogen, donating its electron pair. The hydrogen that is on the acid is the electron pair acceptor. Thank you very much, everyone. In the next video, what we're going to be looking at is how to name inorganic acids and bases. But until then, have a good one.